Hi all, welcome to Math 141. This is our first section, 1.1, Functions and Function Notation. I'm going to start with some definitions to kind of get functions going. First one's a relation, and a relation is just a set of ordered pairs. And then ordered pairs are the x, y, like when we were graphing things back in the day, and we'd graph x is 2, y is 3. So that's a set of ordered pairs. And that's all a relation is. A function is a rule that associates each input with exactly one output. And so it's still this ordered pair idea, but it's this for every x, and this sentence reads really hard. So my little version of it is, for each x there's exactly one y. For every input you only get one output. For every x you put in, there can only be one answer. So that's what a function is. Whereas a relation, I could put in x is 2 and I might get y is 3, 7, and 12. But for a function, if x is 2, y can only be one thing. And the rule part of this, the idea of that is that we have these basic functions and I can apply kind of different things to them to make them do what I need. So if you take a basic linear function, y equals x, a function rule would be something like, if you think about if you had an hourly job and how much money you make an hour, say it's 15 bucks an hour, then your pay would equal 15 bucks times the number of hours you work. And so this is a function, the input is the hours, the rule would be the 15, we multiply by 15, we multiply the input by 15, and what that gets us is our pay. So that's just a little simple example of a function rule. So the rule is multiply by 15 to figure out how much money you're going to make. And we'll have all these basic functions, like this linear one, that we could do stuff to, and then make them more useful for situations. Domain and range. So domain is the set of the inputs. So like in this example, it would be the hours. So the range, I gotta be careful with my words there. The domain would be the set of values that you could put in for hours. So I guess between 0 and I think there's 168 hours in a week. So that would kind of be your domain. And then your pay is going to be if you made no money to however much the maximum money you could have made. So it's the outputs. And we'll see a bunch more domain and range in the next section. So our first example goes, does a relationship represent a function? So this is going to focus pretty much entirely right there. So if I put in 1, I get A. I put in 2, I get B. I put in 3, I get B. So that 2 and 3 might seem a little suspicious, but if we go back to the rule, if I put in 2, I only get B. If I put in 3, I only get B. So that's holding with the rule. For each input, there is only one output. It doesn't say it can't be the same output. It's just there only has to be one of them. And then for if put in 4, you get in C. So we'd say, yeah, that's a function. That one works. If I look at B here, I put in 1, I get A. But you can see when I put in 2, I get B or C. So when I get more than one answer for getting input, that's where, no, it's not a function. So this is the same idea, just kind of giving a little bit different look at data. So does a relationship represent a function? So we can kind of scan through x is 2, y is 3, 5, 6, 0, 6, negative 3. So there's no duplicates in x here. I got totally independent x values. And so that means there's no x where there's 2 possible answers. So we would say, yes, that one is a function. But then if we look at this one, when x is 5, you see how the 5 shows up twice? So when the x is duplicated, it's not going to be a function. Because when x is 5, it could be 3, or when x is 5, it could also be 6. So that makes it not a function. Same thing, but instead of as ordered pairs in a set, now it's just a table. And if I just kind of scan down my x values, I say I don't have any duplicates in x, which means I can't have more than one possible value. They're trying to fool you here a little bit with these duplicate 7s, but when x is 2, y is only 7. When x is 3, y is only 7. So because for an input there's not 2 different outputs, it's yes, it's a function. And then this one, there's those suspicious negative 1s. So when x is negative 1, it looks like the output could be 7 or 5. So that's a big old no for that one. Okay, for this next round, we get function notation. And in theory, 141 isn't your first math class, and so you should have hopefully seen this somewhere back there. If you took 95, 98, or 102, you did some work with function notation. Hopefully you remembered a little bit. So function notation, we have this x and f of x thing. So back in the 90s, we'd write like y equals 3x. I can write that same thing in function notation, saying f of x equals 3x. And this is just a for instance. So f of x is kind of like the new y. Everyone hates f of x when they first meet f of x. I hated f of x in 141. It ends up being huge. It's like super important, and the sooner you can get kind of comfortable with that notation, the better off it'll be for you. It doesn't go away. It's going to stick around for all the calculus. So I would suggest trying to make friends with it. It ends up being really handy. You can give a lot of information, a lot of directions with very little notation that if you tried to explain it in words would take just a ton of words. It's nice for naming things. It's actually pretty useful. So try not to like just resist it like I did. When we have f of 4 like this, where the 4 is replacing the x, and again, this function has nothing to do with this table, just double checking it might. Nope. But it's just an example. So if this 4 was replacing x, then it just is saying that x equals 4. So what this question is really saying is when x is 4, what does the y equal? So we're trying to figure out what y is. And this is, I'm going to cross this out just so people don't think I'm actually using that function. So this question is referring to that table. So when x is 4, we come over here, and the y value associated with 4 is 14. And that's all it's asking you to do. So when x is 4, find y. This one, f of x equals 10. See, now I'm sorry I crossed it out, because the 10 would replace f of x. So hopefully, since f of x is 10, that's this side. So then you can kind of see we would have y, and we were trying to find x. So this, the way you can think of this is y equals 10, so then x equals what? So if we just scan through for where the y is 10, it looks like the x that makes that happen is 3. So x equals 3. And notice going this way, I can get more than one answer, right? Because I can have, you know, the output be 10 when the input is 3, the output be 10 when the input was 4. So when you're looking for x values, you can have more than one that makes it happen. But when you're looking for y values, that's that function thing where there's only going to be one answer. This one is the same idea, but now based on a graph rather than a table. So solve f of x equals 9. So remember, f of x is like y. So this one's saying when y is 9, what x made it come out to 9. So I can come over to my graph here. Looks like y is 9 right there. Kind of tracing over, it looks like at x equals 2. And then evaluate f of 0. So f of 0 means that x is 0. So if I plug in 0, we're evaluating at 0. What do we get out for y? So if x is 0, it looks like right there, the y would be 1. Okay, similar idea with the notation, but now we're doing it more algebraically. We're given an equation. So f of -5 means to put in -5 everywhere there's an x. So this just means x equals -5, essentially. Go solve. So we'll do -5 quantity squared. Let me pause right there. On a calculator, and some people will put -5 squared in the calculator. There's two different things with this that look very much alike. There's -5 quantity squared, and there's -5 squared. -5 quantity squared is 25, because this one is, I could left myself a little more room, I'll go backwards on it. -5 times -5. So we got double negative signs, the square is operating on the negative, so that's going to be positive 25. Sorry, terrible notation there. This way, this square is not operating on that negative. A way of thinking about it is pretend you had -3 times 2 squared. That square is only working on the 2, not the -3. What this really is -1 times 5 squared, and that is 25 times -1, or -25. So these two get confused a lot, and then that's where you kind of end up getting a sign error. Anytime we're plugging in, and there's a lot of that in this section, it's the kind with the parentheses. The sign's getting squared. So if you're putting it in a calculator to evaluate, say it was a tougher number rather than 5, make sure you get the parentheses around the number and the raised to the power to get it to come out the correct sign. Okay, anyhow, back to this now. So plus 9 and then negative 5. So just a reminder, since I went on a little thing there, I'm putting the negative 5 in for all the x's. And plus 11, evaluating. So this is going to be positive 25, like I just talked about up here. This will be negative 45, and this will be 11. And then if we add those up, looks like it comes out to, I should be good and be writing my f of negative 5 over here. Looks like it's negative 9. So when I put in x's negative 5 into this equation, the output, the y value, what we're used to thinking of it as, is negative 9. This next one, it's f of x equals negative 7, so that's like the y. So that's this side of the equation. So we're basically, since this is negative 7, we're just going to put it right in there for that, f of x. So negative 7 equals x squared plus 9x plus 11. So then quadratics, got to remember with quadratics, we got to get them equal to 0 and then either factor, or later in the course we could use the quadratic formula or completing the square. But right now we haven't reviewed those, so it'll just be some sort of factoring. So this is now 0, x squared plus 9x plus 18. And this is the nice kind, so it leads with just an x squared, so I can just set up my parentheses. And I have to ask what multiplies to be 18 and adds to be 9, was how we worked on these. So this would be a plus 3 and a plus 6. So in that case, x would equal negative 3 or negative 6. In case the factoring that I just did there, if you're like having this moment of, ooh, I don't know how to do that, you really need to know how to do that. And I have a video up. If you go 095, if you look at the playlists, and look under Math 094, and it'd be section 5.6 is the one that you want. And these are the newer videos. I have some older ones up, but look for the ones that came out in 2018. If you find an older one, it used to be section 6.6, but just so there isn't confusion. And in this one, there's 6 kinds of factoring, ways to factor, and I kind of go through them all just as a little review. So if you need review on factoring, and if you don't remember how to factor, you need to review on factoring, go back and watch this one and see if hopefully that rattles loose some of those cobwebs on it. The 5 videos that come before these are all the single methods, so you can go back if there's one in particular you weren't great with, you can go back to one of those and watch a few more examples. For C, f of k, why we would ever want to do this, we actually do want to do this sometimes, it's basically just a variable change. So f of k is just going to equal this equation, but instead of x's, it'll be k's. Whatever goes in here is the new x. So when it was negative 5, it just became negative 5. Now it's k. So it's just going to be k squared plus 9k plus 11. This one is a little bit more dastardly. F of k squared plus 2. All of that mess is going to go in for those x's. So this will look like k squared plus 2 squared, and then plus 9, and then k squared plus 2, and plus 11. And unfortunately, we got to clean this up a little bit. I'm about to use the technique from Math 94. This is section 4.6, special products. If you don't know this little technique, you should go back and watch special products also. So this is the a plus b quantity squared. So I'm just going to do the a squared 2ab b squared thing. If you don't know that yet, you can also do this by FOIL. So what I'm going to do is the exact same thing as if I wrote them side by side and then did all my first, outer, inner, last. This way is the thing where you have a plus b squared and a squared plus 2ab plus b squared. So I'm using that formula. This is really handy. If you don't know it, I'm going to do it in a bunch of times in these videos. This is probably the one and only time I'll stop and kind of point out that that's section 4.6 from 2 quarters ago. But it's a very handy little trick, because you just look at this and you just go a squared, okay, k squared times k squared. That's going to make this k to the 4th 2ab, so k squared times 2 times 2. The middle's 4k squared. B squared is the 2 on the end is the b, so 2 times 2 makes 4. And so you can very quickly and easily FOIL these out, and we run into a lot of them. So I'm going to distribute my 9s. That's 9k squared plus 18, and then plus 11. And then I got some like terms, so let me finish that off with k to the 4th. I have some k squareds there, so that's going to be 13k squareds. And then 4 and 18 and 11s, that's what, 29, 33, I think. There we go. Okay, this next one is similar, but it's just a different function that we're working with. So f of x plus 2 is going to equal 2 over x plus 2 squared, because this is going to go in right there, plus 3. And then this is another one of those ones where we expanded out. So that's going to look like x squared, x times x, and it goes 2ab, so 2 times x times 2, so that'll be 4x, and then 2 times 2 is the b squared for 4, plus 3. And then 4 and 3, I can combine those and get x squared plus 4x plus 7. So these look really similar, but they're kind of a different deal. This one, the x plus 2, the 2 on the inside, it's going in for x. This one's literally f of x, which is this thing, plus 2. So it would just look like 2x squared plus 3 plus 2. If it's helpful, you can, and the thing is with this plus, we want to get it probably over a common denominator that's just generally considered a little bit more simplified. So if it's helpful, you can think of that as 2 over 1. And then what we're going to do is just multiply by x squared plus 3 over itself as a clever form of 1. And that's so that we can add the fractions. And this is just like adding, if I had 1/6 plus 1/3, I need to bring this up to 6s, right? So I would do 2 over 2. That's all I'm doing here. And then that's going to look like 2 plus 2x squared plus 6. And now that's all over x squared plus 3, because we have a common. And then combining those, I'll get 2x squared plus 8 over x squared plus 3. And then technically we should see if this simplifies. It doesn't. X squared plus 3 is prime, so I can't cancel. But you do have to at least check. And then C is f of x plus h. We're going to see this in the next section with something called the difference quotient, and that ends up being quite a thing in math. It ends up being the basis for first quarter calculus. So for this, though, we're just practicing with function notation. So I'm just going to put x plus h in for that x. So it's a lot like this one. And then again, we're just going to expand it out. And there's not much to collect on this. So it's just going to look like 2 and then x squared, 2 times x times h. And then h times h is h squared plus 3. And again, this is how I'm getting from here to here is section 4.6 in 094, if you want to go back and review that. So number 7 is similar, it's just a root function now. So our first one is to evaluate. So f of negative 3 is the same thing as just putting in a negative 3 for that x squared plus 3. And then from there, we can just clean it up. So negative 3 makes positive 9 plus 3. And that will make a 12 under there. Remember with roots, and this is section 9. Actually, it's now 8.2 in 095. The old video is 9.2. How to simplify roots. So what we need to do is look for the largest perfect square that divides into 12, which in this case is going to be 4. So 4 times 3. And we can think of that as square root 4 times square root 3. Square root 4 makes it 2 and a root 3. So lots of that 094, 095 kind of shows up in little places in this course. So hopefully everyone's solid in their intermediate algebra. This one, just plug it back in. I kept doing x plus 2s. I probably could have picked a different value, but so x plus 2 squared plus 3. So then that's going to make, and we can't take the root because of that plus 3 on the end there. So all I can do is expand it. And it's going to do the same thing because it's the same plus 3 as last time. So x squared plus 4x plus 4 plus 3. So x squared plus 4x plus 7. I can't factor, so there's no chance I can take the root of anything. Okay, so this next part has whether or not a function is one-to-one. And one-to-one is going to matter when we're doing inverse functions a little bit later. And a function has to be one-to-one to do lots of things to it in calculus. So knowing that it's one-to-one ends up being important later in math. So remember that a function is, for each x, there's only one y. And so for a one-to-one function, it's kind of the reverse. For each y, there's exactly one x. And so it's a specific kind of function. So there's things that don't do that that are functions, but the one-to-one is something particular about a kind of function. So looking at this, for the tables below, is y a function of x, and are they one-to-one? So is y a function of x, is it a function? And if it is it a one-to-one function? So we look down the column of x's, there's no repeats, so for each x, there's an independent y value, right? So we would say, yes, it's a function. But so now we're going the other way and saying for each y, is there only one x that can make that happen? And that would make it one-to-one. But in this case, no, because you see how I have these ones here. Y can be 1 when x is -1 or 1. So the function is not one-to-one, so that's a no. This one we got no repeats in x, and so that means these are all independent for these x's. So yes, it's a function. And then on this one I have no repeats in y either. There's no value that shows up for more than one value of x. So this one we would say, yes, it is one-to-one. And what, like I said, that will mean is that the function is going to have an inverse as a function later in the section. Okay, and the last thing we're looking at in this section is vertical and horizontal lines tests with graphs to determine whether or not the graph represents a function and whether or not the function is one-to-one. So for a vertical line test, it basically says that if I draw a vertical line and I can only hit the graph once, that's going to make it a function. And the reason is, here you can see when x is 1, the only output is 2. Anywhere I draw a vertical line, that's going to be the case, because for this given output, or this given input, that's the only output. So we would say, yes, that's a function. Same thing here. This one, it starts looking a little vertical, but what it's doing is getting closer and closer to the y-axis, and so it would pass the vertical line test. So we would say, yes, that's a function. This one is doing all kinds of curvy things, but wherever I draw a vertical line, it wouldn't matter. I only hit it one time, so that's a yes. And this one is also a yes, because, again, I only hit the graph once. I should probably have one on here that doesn't pass. So an example, I'll just do a quick one over here, would be a circle. If I draw a vertical line, then for this x value right here, whatever that is, there's 2 different y values, and so that would be not a function. The second thing we're checking on these graphs is it one-to-one, and that's going to be a horizontal line test. So I'm going to start down here with the one that isn't one-to-one, just to kind of show. So you can see if y was 1, it would be 5, x could be 1, or a little bit past it, a little past -1, -5 again. So for that given y value, there's 4 different x's, and for a function to be one-to-one for each y, there can only be one x. So this we would say no. This one would also be a no, because I can hit it more than once. This one I can only hit once. These are implied that they are going to approach forever but never touch, so this we would say yes, because anywhere I draw a horizontal it works, and likewise this one would be a yes. For the 3 questions at the end of the homework for 1.1, those are going to go with the next video, which is going to be called Library of Functions. And it kind of bridges between 1.1 and 1.2 and some later material, and it's a little bit of stuff. So I'm going to do that as a separate video.